When you design a new custom logic and you want to incorporate it in your SoC, you need to follow certain procedures so that the processor can actually communicate with this new custom logic and the rest of the I/O cores or any of the other logics doesn't interfere with it and it doesn't interfere with their operations. So what I'm trying to say here is you can't just take a custom logic and throw it in the SoC and hope it works. What you need to do is you need to connect it to the bus. And in order for you to connect it to the system bus of your SoC, you need to understand your system bus and figure out what components it takes and doesn't take. And then you will actually create some sort of a wrapping circuit around your custom logic. And the purpose of this wrapping circuit is actually to facilitate the communication between the processor and this custom logic. So when the processor needs to control this custom logic, it can actually issue some sort of a write command and it writes into it, and of course it will issue these write commands through the bus. So this particular wrapping circuit here in blue or wrapping circuit in blue, it's actually just going to interpret and facilitate this particular action. And the same exact thing, maybe the processor wants to read something out of this custom logic all the way through here the bus. That wrapping circuit will allow us to do this. So the ultimate goal of this wrapping circuit is to facilitate reading and writing into and from this custom logic. And this custom logic could be anything you can think of, whether it's just a simple pattern detector on an input, or maybe it facilitates serial communication between two subsystems, or just communicate LEDs, whatever you can think of. We're not going to care what this custom logic is. What we care about is the processor sees it as a bunch of registers, and we're creating some sort of a wrapping circuit so that that processor can actually read and write from it. However, in our system, we actually have multiple of these custom logic cores. So we will facilitate, we will do it in such a way that it's really systematic. So all these wrapping circuits kind of look the same. They have the same exact signals, inputs and outputs, and so forth. And because we have so many of them, we will have another wrapping circuit, and this is basically the system level one, and we're going to call it the MMIO controller. We're going to cover this later because it's just basically an expansion of this particular wrapping circuit. And again, the purpose of this particular one, system level, is so that I know that the processor is trying to communicate with a custom logic, so it knows which custom logic it's trying to communicate with, and it just activates one of them, not all of them, because the processor is trying to do this. And the way we construct the system level one is extremely similar to the smaller one, so we're just going to focus on the smaller one for now. And the way I'm going to explain it is with a simple example. So we're going to have we have a system logic in here, or a custom logic. And because I don't want to draw so many wires and arrows around, so we're going to simplify things a little bit here. So we're going to assume that our address in here, which is on the address bus, is actually exactly 8 bits. And because we know that we have 64 possibilities for these I/O cores, we're just going to keep this assumption. We know that six of these are actually to choose the core, and those will be used by the system level decoding, which is basically right here, okay, to choose the core. Okay, so what's left is actually out of the 8 bits, we're gonna have 2, and because we only have 2 bits left, that means I only have 4 total registers. 2 to the power 2 is 4 registers for this custom logic, as opposed to 32. So I don't want to just show you 32 registers for this custom logic, but we know that in our particular system, every custom logic has virtually 32 registers. Whether it uses it or not, it's a different story, but it technically has 32 registers for it. So what we're seeing here is the first part of it, which is, let's see how can we write into the interface. And I'm writing here decoding because, as it turns out, that writing happens through decoding. So how does this happen? Well, here's the deal. What the processor does, it actually places some write data, okay, on its write data at bus, basically. And as it turns out, that this particular data gets actually broadcasted to all of the registers. All of the registers have them at their input, but not all of them are actually enabled at the same time. And not only the registers within this particular custom logic, this is actually broadcasted to all of the registers for all custom logics. So if I have 64 and each one of them has 4 registers, so 64 times 4, this particular wire is actually broadcasted everywhere. So every register you can think of actually receive this particular data. However, it doesn't act on it. What custom logic acts on it is actually specified by the address. So what the address does is the following. We take this particular, the processor puts some sort of an address, and as it turns out, it actually puts these 8 bits. We know that 6 of these are actually to choose a core. We're going to assume that this particular core actually have this particular address, and the system level decoding, which we're not going to cover right now very extensively, but it's actually all it does is just make sure that this is the one address. Okay, let me activate this particular custom logic. So what it does, it has some sort of a chip select. It has actually 64 of these chip selects, we're going to see later, but that particular chip select comes in here and activate my custom logic in here. Okay, so the custom logic now is activated because these 8 bits just match, and then internally, let's assume that the least 2 significant bits of this particular address just happen to be, let's say 0, 1. Okay, just happen to be that one. So these 2 bits in here, so 6 goes to the system level, but 2 bits actually, the system level one actually gets it, but outputs it as is, and then it goes in here. So now I have that particular address, which is 0, 1. And this address is actually going to a decoding circuit. It's just a normal decoder. So this normal decoder technically takes some sort of an input and an output. And you will see that later that these write and CS are just to enable that decoder. And you can see it here from this particular truth table. But for now, I know that the address is actually the input for this decoder. And this actually indicates that I'm interested in register number 1. So I am interested in this particular register. And the way it's actually going to do it is actually going to take this particular register in here and just activates it and put in 1 in here. So what I'm effectively doing, I'm enabling it. Okay, so again, it does have the right data in here, and when it gets this enable actually gets asserted, you will see that whatever the processor tried to write into it, it's actually got written into this particular register, and now the custom logic has access to it and actually can do something based on this value of this data. Maybe this register actually, because you wrote into it, maybe it displays this. The custom logic is just to display it on an LED, for example, or maybe to send it to another custom logic or another system. Okay, so let's talk a little bit about these 2 signals. So the system level decoding, it took actually the least or the most significant 6 bits, figured out that this is actually the custom logic, or this is the core I'm trying to get to out of the 64. It issued a chip select into it, and the write signal. And again, the write signal is actually issued to all of them. It's actually broadcasted to all subsystem. All of them have it. But only when you issue a write command and the chip select for this particular core are together asserted, this decoding circuit works. And this is what you do see in here. So what you do see in here is the chip select is 0. I don't care. The output will be 0. So all of these enables will be completely 0. Nothing will happen. Whether the write is 0 or 1, I don't care. Now, if I chip selected it, but the write is 0, it's also the same. This decoder does not output anything. So these 2 here are basically the enable for this particular decoding circuit, and that's what it does. So again, it's very simple to write something from the processor. You're going to have to decode your way through it. And generally speaking, this decoding happens on 2 levels. The first one in here and the third one in here. I never said that there's a decoding in here, but this is effectively what's been doing. It's actually going to decode the most significant 6 bits, and then it's going to decode the least significant 2 bits. In our case, because we have 32 registers, it's going to decode 5 bits, and it will activate which one of these 32 registers we have. Okay. We move on to the write or read actually interface, and this one is not using decoders, it's actually using multiplexing, but the concept is similar. Now I'm trying to get from the custom logic to the processor all the way through, and the way we do it is, again, the processor doesn't put anything on the read data. It's actually trying to read it from the IO core. What it does, it puts in some sort of an address in here, and again, the address, we're going to assume that it's 8 bits for simplicity, so the 6 of these bits will actually go to the system level in here. And the 6 bits basically will tell me which one of the cores, and let's assume that this is the core I care about. What is it actually doing? Let's take a look at the internal one, which is actually more interesting. Let's assume, again, I'm interested in 0, 1 like before. So this address of 0, 1 goes to the selector of a multiplexer. It's a multi-bit multiplexer because each one of these registers might be 32-bit or 8 bits, whatever it is. Let's say it's 32-bit. So what it's doing, it's actually putting that means I am actually taking this particular signal that is coming from here all the way and mapping it to the outside. Remember, this is what the multiplexer does. So effectively, what's it doing? It's actually routing the internal, this is 0, this is 1, basically this register, it's routing its input all the way here. And the system level decoding is again another multiplexer that is actually taking the following. It's taking these 6 bits and activating it, and the rest of them here are actually connected to the multiplexer from the other cores. So each one of these cores will have a multiplexer at its output, and that multiplexer at its output have that. So, and they're all connected to the second multiplexer. So reading is actually happening as opposed to writing in a couple of multiplexing steps. So the first one is the internal register multiplexing, and the second one is actually the core multiplexing. So I have 64 of these in here, and based off the 6 most significant bits of the address, it will actually get decoded. Okay, it's pretty simplistic. So we take this one in here, gets mapped in here, gets mapped in here, gets mapped in here, and then the processor actually issues some read signal. So there is a read signal that I'm not showing in here. There's actually the processor issues some sort of a read signal. I think it's called an FP_RD. And this particular signal will be connected to some sort of a register in here, will activate this particular code again. Or it will activate it. It's similar to how we did it with the read. It will actually activate this particular core in here as opposed to activating all the other cores. So just make sure that the other cores are not activated.